Nice to have you all here to our presentation on TOOP, the Topology Optimization Initiative at Elia Group. I'm very happy to be here again, because this is actually the second time I'm on this stage. Well, not like physically this stage, last time it was in Brussels, but last year at LF Energy, we were there. We presented where we were back a year ago, and it's been a year, and a lot has changed, and very glad to be here to present to you a GPU-native approach of tackling grid topology optimization. And I will first start with who we are. I'm Nico, and this is my colleague Leon. We are from Elia Group. Elia Group is the TSO incorporating East Germany and Belgium. So we're basically two TSOs fused together. And this project is also a project run by both TSOs. So we have two clients for which we develop this, two control centers in which it needs to work, which already is a great setup to start with. And before I dive in, I also want to lose a few words. You've already heard about it today, but we have this initiative called MCCS, the Modular Control System Software, where we also integrate it. And the idea behind MCCS is basically to write a platform for different modules. That's the M in this MCCS, that stands for modular, for different modules in our system operations to integrate, to join together. And we have SCADA system aspects, we have grid control aspects, but fundamentally we also have grid analysis aspects and grid optimization parts where we slot in. It's a very big initiative. If you want to learn more, I invite you to check out the website. There's a QR code. But now let's dive in a bit into topology optimization. I first get a look at what is TOOP, what is topology optimization, get you all briefed on this. Talk a little bit about our tricks, how we made it work, and how they're very different from what everybody else did so far. We have a demo, so I would like you all to cross your fingers. Putting a demo on stage is always bound to fail. We will see if it bears with us. Because this is an open source conference and we have our hearts beat for open source, we will take you on a journey on how we try and work on getting this project to be an open source project. And a little bit what you can expect in the upcoming weeks or months. But before I start, who of you knows or has an idea when I say topology optimization? Who of you has an idea what I'm talking about? Oh, great. Okay, there were a few people who didn't raise your hands. You will hopefully raise your hands the next time you're asked. So I will tell you a little bit about it. Who of you is working with topology optimization? Okay, that's... Wow, what an audience. Wonderful. So for those of you who don't know about topology optimization, the basic problem that we're trying to solve here is we have a grid that is congested. So we built it 40 years ago. Obviously, the best thing would be to build more grid, but building more grid takes time. So we need to do something about congestions now. And otherwise, they will melt our power lines. And what we used to do, or what we do a lot, is something called redispatch. The idea there is you shift the generation on the grid to make it more beneficial to the grid. But that's a costly operation. And what I mean with costly, it costs multiple billions of euros every year. So this is a massive amount of money that we are losing here as a society. And what can help with this are grid-related measures, which are essentially cheap, like opening or closing switches. The problem with these switches is there's quite a lot of them, and there's combinatorics. So it's very hard to find a good topology, because we have enough switches on the grid to have like around 10 to the 120 feasible topologies we could go to. That's more than atoms in the universe, so we will not have time to talk about each and every one of them, but I can already tell you that of these 10 to the 120, most of them are completely nonsense. And we want to find the gems in this massive search space. And because this is such a massive search space, this has not been really solved yet. To my knowledge, it's just right now that we are seeing the advent of the first scalable, viable, performant enough solutions to work on a full-scale grid. And we are one of them. And to those of you who know about topology optimization, when I talk about topology optimization, I mean we do transmission line switching. That's basically the optimal transmission switching paper from 2008. But we also do bus splitting and reassignments, which means in the substations we can shift around our interconnectors, open busbar couplers. And we are working on reconnections, basically the inverse of transmission line switching, canceling maintenances, and PSTs. So with this, that's basically the thing that I talk about when doing topology optimization. And this combination makes me so excited because it's a relevant problem. It's super expensive. It's a big impact to society. Lots of carbon going out in the world, which doesn't need to be there. And it's hard. So me as a nerd, I'm hooked. That's the two things that get me. And what we did over the last 2 years was build a product to solve topology optimization. And we have a product now. It can run on most data formats that are common in the industry, thanks to PowSyBl for implementing a CGMS and UST importer. Then it can, it has a user interface by now. Last year, when we were presenting, we had Jupyter notebooks. By now, we have a UI. We are fast, so we have a time horizon. Operational topology optimization needs to happen within less than 1 hour. And in this time, it needs to be a human-machine interaction happening. So we have around 15 minutes to run an optimization. By now, we're down under 10. We are a QD-based approach. QD stands for quality diversity. If you don't know what that is, it doesn't matter. The point of this is that after the optimization, we can still perform multi-objective trade-offs. So we can still choose a topology after the optimization finished. We don't get one results. We get a set of them, a Pareto front. And we can do a multi-objective trade-off when the optimization has finished. And we, by now, implement most of the constraints that bug our operators. I won't say all, because that's certainly not where we are and where we will ever be. And there are some constraints which are just fundamentally very hard, like dynamic stability. But yeah, we have done a lot of work on getting to the point that our operators are more or less happy. And at the core of this, you came to this presentation and you wanted to hear something about GPUs. So let's talk about GPUs. GPUs, the main driver of the AI hype, they have basically enabled GPT, whatever, but they also enable us in the grid. If you look at DC load flows are basically linear algebra, just matrix operations. And GPUs, they eat matrix operations for breakfast. So what we did, we ported a DC solver fully onto GPU, so we never leave the machine. With this, we reach 1 billion load flows per second on one GPU. Huh? So 1 billion load flows per second, that means we can do multiple 100,000 n-1 analysis every second. And if you press n-1 analysis in Power Factory, even in DC, you will not be finished in 1 second, no matter how large your grid is. So we have this massive performance boost of around 5 orders of magnitude over commodity solvers. And it's even scalable. So we can, if we go for larger grids, we can just add more GPUs. It just scales linearly. With this at heart, we basically plug the most simple of all optimizers on top, just a random search with a bit of extras. But like if I talk about quality diversity genetic algorithms, there's basically just a random search. We just randomly flick switches until something good happens. And yeah, this is not the strategy that you should do on the live grid, but in simulation we can do it. And because we can do this a lot, with 1 billion load flows per second, we can do a decent amount of topologies every second. We have the performance to search a large space of these 10 to the 120 possible candidates, large enough that we get a good solution most of the times. And there's a bit more tricky things here happening, especially the map elites part allows us to do like these trade-offs post-optimization. But fundamentally, we have the simplest of optimizers. No interior point, no simplexes, no complex mathematics, just randomly trying things out, but very quickly. And this is where we were last year. By now, we have a full pipeline. So we have an import stage which is mainly driven by open source tools. Pandapower and PowSyBl help us a lot to get our data into the right formats. We have this DC optimization with by now a lot more constraints than last year. And we also have a very working AC validation, because we don't want to show the operators anything that's been validated on DC, because there's a DC-AC gap. It might be up to 10% off. What we see is for thermal constraints, so for overloads based on power, these DC-AC mismatches, they're actually not so bad. They go in the right direction. So for some reason, somebody came up with this DC linearization, and it's actually pretty good at predicting active power flow on the grid, which for us TSOs is one of the main causes of congestion. But when we have congestions that are very reactively driven, we're actually not that good anymore, because we are optimizing on DC, and then later in AC we find out, yeah, that's actually not working what we did in DC. So for thermal constraints, this works quite well. For thermal problems, for voltage, well, we have to do some work. This is our right now architecture, and we have a lot more tricks there. If you want any details, I can definitely give you some details, but for the sake of time, you all have this question in mind here. How good is it? How good is it? And for that, I already told you we are fast, so we managed to get this whole process down under 10 minutes. And we are already integrated in one of our 2 control centers. So I told you we are project aiming to make a product work at 2 operating centers at the same time. In one of them, we are already almost there. And I want to tell you the story of the 7th of July this year. That was our official release day when TOOP was offered for the 50 Hertz site into the control center. And we had a date with some people, and among others, there were 3 operators who do manual topology optimization every day. So we went into that room, all our team came, we were all very nervous, did some high-level presentation, and then we went on to show our product, our demo, and we showed a topology. And showed them the congestion, okay, there was some problems in some part of the grid, and there was a congestion, and then they looked at the results, and they said, no, we're never gonna switch that. Okay, so couldn't go better, huh? Couldn't go better. After 2 minutes, they said, no, this is not possible. We can't switch this. Okay, but then let's go on. Let's at least explain to us why you can't switch that so that we can fix it. And we had a look into the topology. We had a look at load flow results at certain substations. They opened it in the established tools. And after like 20 minutes, one of the operators told us, well, to be honest, I can't tell you why we don't switch that. And that was exactly the moment I was hoping for. The moment where we offer something that they didn't come up with. That's like the definition of AI. The machine has found something that the human did not come up with, and that's not like that's a potentially viable solution. And that's the point why we do this. So I would claim by now we provide value, but I do not claim that we are perfect. So you put a techie on this stage, you don't get the shiny presentation, everything works. You put a techie on this stage and you get a realistic thing, what can we do, what can we not do? So yes, we do provide value, but we're definitely not providing value for every single problem. We have failed in multiple topologies where there would have been a solution. So we still have work to do, especially when it comes to like voltage-based or stability-based problems. And we also have plenty of bugs available, so there's definitely not the fully fledged product, but we are an MVP, and we have managed to find a realistic topology that the operators have not found. And that's basically what we set out to do. And now comes the part where you need to cross your fingers, huh? You did cross your fingers, right? So I hand over to my colleague. How do I get this over? Yep.
Oh, yeah. Great, thank you, Nico. I can now show you a sneak peek into our modular control center. So what you would see as an operator if you would open MCCS right now. And you would start right here. You can choose one of various modules for grid analysis, for example. And now, of course, we want to show you the topology optimization. What you would do first, thank you. What you would do first is choose a time step you want to optimize because you know you have overload at this hour. And then you select it and choose some importing parameters, what kind of grid model, what process, what n-1 definition you want to use. And choose some optimization parameters, how to penalize certain occurrences, how long the optimization should run, stuff like that. Most of it predefined by us. And then you would start importing. Then you wait 10 minutes or so. Of course, we don't have the time right now, so we prepared an optimization beforehand, which you can see here. Let me make it larger. Yeah, exactly. We had one time step optimized for this. Just an example, time step with mangled data. And you could look into the details of this one. And then you would see a bunch of topologies we are proposing, all validated in AC, so a whole contingency analysis run on them. And for each topology, you would see at a glance some values. So how much overload energy remains in the system, what is, how many switches do you actually have to flip to get to this topology, which substations are affected or which lines you disconnected, and how much is the highest overload afterwards. Then, depending on how adventurous you are, you can select one of these topologies. Maybe at the beginning, you only want to split one substation in your system. And then you see, for example, this one, only one substation split, but you were able to reduce the overload from 2 gigawatts down to 300 megawatts already. And then you can also see some more infos on which critical branches and which critical outages led to this result. And you can see the substation setup. So here you can see how it was before and what you changed. And of course, you opened the busbar coupler as well. So now, or before, all the lines were connected, and afterwards, only the lines up here were connected to the lines down here, and vice versa. You can also look into more detailed load flow results and see, okay, how was it before? Probably hard to read for you, but the first line was reduced from 190% overload down to 90%, and the same goes for many others. So that's where the overload reduction comes from. And then the operator can decide, okay, this looks feasible, I would like to implement this, so I will import this into my source system, Amica, Power Factory, whatever, reevaluate everything, and then propose it for the day ahead process, and hopefully reduce the redispatch that has to happen. Or you don't like the topology, and you tell us about it and why you don't like it, and then we will try to find a new metric to include into our optimization. Or you look at another one, that's also possible, of course. Yeah, so that's it for a small sneak peek. I just close, reduce it. Yeah, maybe this is safer. Thanks. Yeah, that brings us to the road ahead. So we still have to do a few steps until we are completely production ready. Some security assessments we still have to do, some more integration questions. How do we set up the data pipeline to get the European grid models directly into MCCS and into our optimization, stuff like that. So yeah, some stuff to figure out, but it's already working so far. And then there are some technical features. For example, reconnections, because so far we only disconnect lines, but in practice the operators often like to reconnect lines that are currently in maintenance, but not super urgent. So for example, if you just want to paint a tower, but by reconnecting the line you could save a few 10,000 of euros, then you would probably just paint the tower a week later. Another thing is, Nico already mentioned the voltage constraints. So we are looking into various low flow solvers that are fast, but also give us info about the voltage in the system. So we already can optimize on this during our GPU run. And another thing is the optimization of phase shift transformers, where we recently finished a master thesis, which we can now also optimize on the GPU. And finally, also the integration into redispatch, because it could happen that we reduce the overload energy in the system, but now the overloads are in a part of the grid where we actually don't have any power plants to redispatch, so it might actually increase the amount of redispatch we have to do. So those are things we have to figure out. And yeah, last but not least, the multi-time step optimization, because we don't want our operators to flip switches all the time. So we would like to find a topology that's actually valid for multiple time steps. But so far, we assume that if you optimize one time step, then usually in the next hour, the situation is similar-ish. So the topology should still work. And then one of the more interesting concerns for you probably at the summit is our open sourcing journey, where we put a lot of effort, or especially Chris, in the last 2 years. So I will get you into our journey that happened over the last 2 years. So in the beginning, it was mostly Nico, writing lots of code, getting good results quite quickly. We started a collaboration with Tenet at the same time, and then we were really eager to get results, and we saw good results quite fast, and we were really hyper about it. And we were thinking, okay, let's share this. People are interested. Let's just open source it. How hard can it be? So we asked ourselves, okay, how do we do this? And nobody knew. So there were no processes. Who do we even have to ask? Who has done this before at 50 Hertz or in the ELIA group? No idea. So what happened was lots of lobbying inside our company, lots of explanation of the value of open sourcing, why we want to do it, what are the benefits, and so on. I guess you heard a lot about it at this conference. And yeah, then lots and lots of emails, meetings, and talks, figuring out who to talk to, legal, security, regulatory affairs, the digital office, other TSOs, and that's at ELIA and at 50 Hertz. And yeah, that takes plenty of time to get the ball rolling, but then when it was rolling, something happened in the background, and we were waiting and assuming something was working. Then that took quite a lot of time, but all the waiting seems to have a good ending, because now finally we have our open source project office together with our new open source project manager, Sven Fritsche, and now there's light at the end of the tunnel, and we are hyper once again, and hope that we will soon be able to actually give you our topology optimization as an open source product. And only a few steps remain, hopefully. A few license checks, deciding on what license to do. We are the pilot project for this, so give us a little time. Then there are some committees that probably have to decide, but hopefully say yes. And then we will be the first major open source project in the ELIA group, and we are really looking forward to this. And yeah, looking forward to collaborating with you and you trying out our topology optimization with your grid data that you may or may not be able to share. And yeah, if you're interested, contact either me or Nico or Ben and Chris, who are sitting in the audience somewhere. And yeah, one last remark, we are also hiring at 50 Hertz. So we want to extend our AI grid analysis in our modular control center in the whole ELIA group, of course. And yeah, contact Georg Menser if you are a talented solution architect, data and HPC specialist, etc. Yeah, thank you very much. We are open to your questions now or afterwards.
Thanks. 2 questions, actually. First one, you mentioned you used Pareto front and multi-objective optimization. So you mentioned one of the objectives is to reduce the mismatch that will recur, power imbalance, actually, that will incur a redispatch, I'm sorry. What are the other objectives that are built into the optimization?
Yeah, so there's basically, topology optimization is basically a trade-off. If you open a transmission line or you open a circuit breaker, you demesh the grid. So naturally, you're trading a more beneficial load flow for stability of the system. And stability of the system is a very abstract property. So we can run an n-1 load flow and we see a part of the stability, but there's so much more to stability that we can't ever assess within 15 minutes. There's dynamic stability, short circuit currents, voltages, we can kind of assess a bit. But there's just so much we can assess. So our largest post-optimization trade-off that we do is how far away from the known default switching state do we want to switch. So how far do we want to go? How many switches do we flick? Which is basically a quantity for how much into the unknown do we go. And if we find a topology that is kind of good but doesn't go so far, then it's probably the better topology than a topology that gets you 5% more reduction but has a massive amount of switching. So this is this trade-off between improving the congestion situation but reducing meshedness, reducing somehow security. This is what is at the heart of it, and which is like the multi-objective problem, because these things, they come in multiple facets. So that's basically the trade-off we are doing, and which we can't decide up front before the optimization, where we need the human to also tell us, with this grid situation we have today, we can be adventurous, let's go very far, or with the grid situation we have today, let's be conservative.
That's great. Actually, your answer links to my second question.
Wonderful.
Does the genetic algorithm has favorite victim switchgear to turn on and off all the time from the running, or it spreads out over the grid when you move from time step to time step?
Yeah, if we were to move from time step to time step, so what we found is actually if we just optimize the worst time step within a congestion, we have a very decent solution for the entire congestion. Meaning the state-of-the-art approach is we don't have time. Like, we just have one time step. We want to get there, but we are not there yet.
Thanks a lot.
How large are the typical grids that you try to optimize for? And then also, how do you benchmark?
The second question is a very good one. Let's start with the first one. So for the Belgian grid, we have, well, the size of Belgium plus a bit of area around it. We usually look at 150 kV and above for that. So everything below doesn't really interest us too much. In Germany, transmission starts at 220 kV. So we have 220 kV and above. And we also have an inter-German connectedness, so we look at more parts there. Depends actually which operator you ask. Sometimes they also don't really care about what happens in the rest of the grid. They just look at the IGM. But let's say the better solutions are usually found on looking at wider areas of the grid. And if you want a number in bus bars, around 3,000. Oh, the second question, benchmarks. Yeah, so I'm very happy that we are after the RTE 7000 presentation, because so far there's no good benchmark for topology optimization. There's no good open data that we can use, that we can send to vendors, to research, to academia, to hackers, to see how good everybody is. Meaning, if you want to compare topology optimization tools today, you basically have to listen to sales pitches, where every topology optimization tool is the best one, except for ours, because this is not a sales pitch. And there's no other way to benchmark right now. But I'm very excited for the developments around open data, what RTE has kicked off. And we hope that we can use this as a benchmark and build upon there. But yeah. For now, I have to disappoint you. Sorry, I would like to have a benchmark for you.
That's fine, thank you.
Yeah, I think this is also end of time. Yeah, we are at point time. So sorry, maybe one quick question. I think it's fine, and then we have to hop off stage.
Okay, where is the state estimation in your optimization or your configuration problem?
So state estimation is not part of the TOOP project, not part of the topology optimization part, because we are basically a planning process. Topology optimization in most TSOs happens in some sort of planning stage, and there is no state estimation in planning, meaning we don't have a direct relation in terms of processes, but we are both part of MCCS, so there's also a state estimation effort in MCCS, which works on that. But we are not directly a part of that. It's a separate team. Okay, but now I think I have to cut it and hand the mic to our next speakers.